Hi, we are the Lifespan of Rope Group. I'm Evan Vogan.
I'm Michael Schmalzley.
I'm Moses Chuente.
And I'm Connor Suhowski.
The main question we are asking for our project is, do ropes show a significant decrease in strength when they are more worn? The objective of this experiment is to prove that there is a correlation between rope usage and tensile strength so that we can keep climbers safe by recommending when they should retire their old ropes. In the real world, it is hard to know just how damaged your rope is as a climber because you're not consistently thinking about or really paying attention to the stress you're putting on your rope. Our goal is to do enough research and testing to be able to tell climbers when they should retire their ropes without having to worry about it themselves. We found a study that was done on the lifespan of rope by a different research team in which they tested their rope in the real world by attaching acceleration measuring devices to climbers and comparing the data they got from that to a control rope using the UIAA standard. The difference between what the other team did and what we are doing is that in our experiment, we have much more control over the rope usage because we will be subjecting different ropes to varying ranges of cycles of precise loads we decided on. This is very important because if we do this experiment and are able to show that it is unsafe to be using ropes after a certain point, we can inform climbers of this and keep them safe out in the real world when they may be using ropes that are unsafe and they don't even know it. Some of the things to keep in mind about this experiment are things like the rope's elasticity, as well as the amount of tension and friction on the rope. Some other things that are relevant to this study are the material properties of the rope and the manufacturing process that it was made using, as well as the safety standard that the rope is rated for. We were able to do some preliminary calculations about the ropes that showed us we should be able to find some definitive correlation between the time under tension and the ultimate tensile strength.
To your right is a flowchart of our overall process. We stretched each rope using an electromechanical load cell and subjected it to significant tensile stress during testing. We tested 3 ropes of each color, subjecting 2 to a cycle load of 5 and 10 cycles from 1 kilonewton to 5 kilonewtons, and then tested all 3 ropes to their breaking point. The third rope of each color was only snapped to test its ultimate strength without prior wear or tear. Moving on to experiment conditions. We conducted an experiment using 6 different conditions. The first 3 focus on comparing and contrasting the results of 3 different types of ropes. The remaining 3 conditions involve subjecting the ropes to various loading conditions, including continuous load until failure after 5 cycles from 1 kilonewton to 5 kilonewton, and load until failure after 10 cycles from 1 kilonewtons to 5 kilonewtons. And on your right would be the relevant variables, measurement techniques, and equipment used. Now moving on, not much was done as the Blue Hill software handled the heavy lifting in terms of calibration. We consistently were using the same knot tied by the same person. And in terms of our process, to prepare for the experiment, we tied two double figure eight knots on each end of the rope as closely as possible to account for its elasticity. Then, using the Blue Hill software, we programmed the process and subjected three ropes of each type to testing. One of the three ropes went through 5 cycles of the program and then was pulled to failure, while the second rope went through 10 cycles before failing. The third rope was tested for ultimate strength by pulling it until it broke without any prior cycling. And finally, over here you see the timeline of our overall project. Each day has a description of what came to be and what was accomplished on that day.
This is the budget for our experiment. The cost for samples of rope only contributed to about $44, and the rest was used on steel stock to make the fixturing to hold the ropes. Now that the clamps are made, this test could easily be redone at a fraction of the cost. There are a few risks and hazards that were identified for this setup, but all of them are easily mitigated. The most concerning risk is the action of the rope after it has snapped, as it could hit testers or test equipment as it breaks. This is mitigated by installing a temporary plexiglass shield in front of the load frame, and safety glasses were worn to add another layer of protection. The other hazard is the relatively loud noise the rope makes while snapping, which is mitigated by wearing ear protection. This is the extension and load data from the 10.2 millimeter rope. Notice the 5 cycle test did not snap. The orange line represents load, while the blue line indicates extension. The braking loads ended up being much higher than anticipated. It is also interesting to note the relationship between extension and load. Despite appearing rather consistent on the initial brake, the cycling shows how little the rope needs to be retracted to drop the load significantly. This is the data for the 9.8 millimeter rope. The trends shown here are the same as the previous data, which is to be expected considering the testing procedure is the same. This is the data for the 9.5 millimeter rope, also indicating the same trends as before.
As shown in the plot to the left, the data is inconclusive. More sample testing is needed in order to find a more consistent correlation as well as find a more definitive conclusion. Overall, as seen in the data, the results were imperfect due to the accuracy in the load cell, human error, and with the limited amount of samples to test. Another issue that arose throughout the testing was the knots tied. While tying the knots, we tried to be as accurate as possible with the distance between knots. But our hypothesis is that there were small variations in the knots that could have been the result of the inconclusive results. For the future, more cycles would need to be tested in order to gain more conclusive results. But due to a variety of factors such as allotted time in the lab and the need for more samples, we were unable to do that for the current test. If the test were to be repeated, a machine with a longer stroke and the ability to use the clamps we designed along with a higher top speed would allow us to gain the results we were looking for. We would also like to thank Dr. Hoover and Jacob Weller for their assistance throughout this project. We would also like to thank our TA, Sandeep, for the help and advice he gave us throughout the process of our testing.